Okay, today we're going to start chapter 15 on equilibrium. This is a continuation of kinetics. So, kinetics is what we generally measure at the beginning of the reaction, when mostly what we have is reactants, and we can um, develop a rate law based on the reactants. Uh, but as the reaction progresses and products are formed, then what we're going to see is if it's a reversible reaction where equilibrium can take place, some of the products will revert back to the reactants, and that's called a reversible reaction. So we're going to be focusing on reversible reactions in chapter 15 to reach chemical equilibrium. So there's only 5 sections to this chapter. They're all very important. The first one is the concept of equilibrium. And let me just say, even if you're not a chemistry major, the concept of equilibrium is really important. In biology, they'll call it homeostasis. If you're in wildlife management, it's about predator-prey equilibrium. If you're a civil engineer and you're developing roads, it's the equilibrium of the traffic, how much traffic can go into town maybe, and how much traffic can go out of town at any given time, looking at a cross section of the road. So this equilibrium is important not just in chemistry, but also other fields of study. Then we'll talk about the equilibrium constant, how we calculate it, and then equilibrium expressions. And then we'll have a bunch of problems with the expression. So we're going to be testing your math again in this chapter. And the key to doing well on the math in this chapter is organizing your data, making tables, and then working from those tables. And then the last section, very important, is what factors affect equilibrium. So one of the things we know that in chapter on kinetics is that temperature affects the rate constant. Well, temperature is going to have effect on the chemical equilibrium as well. So that's where we're going in this chapter. So the concept of equilibrium. So here we have a reaction where dinitrogen tetroxide is decomposing into 2 moles of nitrogen dioxide. And so let's just look at that. So here we have it. Here's what I want you to focus on. When you see the double arrows on the chemical yield, that means this reaction can go in the forward direction or the reverse direction. And so if that process is reversible, then equilibrium can be established. And so look at this, what this means. It's the rate of the forward reaction, so we're just going to focus on this part, is equal to the equilibrium, this is actually the kinetics. This is the rate constant times the concentration of the reactant. All right, so we learned this in the previous chapter. All right. The other focus is the reverse reaction. So the rate law for the reverse reaction is rate of reverse equals the rate constant of the reverse reaction times the concentration raised to the experimental rate order. So it's determined to be 2. Remember, this has to be determined experimentally, and it is 2. And so, again, if this reaction is going in reverse, this would be like the reactants, and this would be the product. So remember, rate laws are rate equals the rate constant times the concentration of the reactant. So that's what we learned in chapter 14 on chemical kinetics. And I'm about made a mistake here. How do you know the difference between a rate constant and an equilibrium constant? Equilibrium constant will be a capital K. The rate constants are lowercase k. So that's how you catch yourself in not making that mistake. All right, so let's put these together and let's look at what this looks like. So Again, what we have here is we have initially this substance. All right, so we saw this in the last chapter, and we have zero product. Okay, so initially we have lots of dinitrogen tetroxide. That's what this is. The nitrogen's the blue, the oxygen are the red. As a reaction progresses, we go from a colorless vial or ampule to a very colored ampule. And notice again, not much change in these last three compared to the first two. And it's kind of hard to see that there's not, you can see there's not much change here in these three. There's a little bit, but not much. So in chapter 14 on kinetics, we were focused on mainly this section here and back. And we would say the rate law is equal to what we had for the forward reaction, which is just K times the concentration of the reactant raised to the appropriate order. It's first order in this case. What we're going to focus in chapter 15, 16, and I believe 17 is this part. This part where the rates have become constant. We don't see these dramatic changes in the rates like we see here. The rates have become equilibrium, have become constant. We call this equilibrium or steady state. You'll hear that word as well. And we're going to determine why it does that. All right, so some important rules to remember. Equilibrium is dynamic. A lot of people think like, okay, let's go back to the last slide, that this is a static image, and they say, well, it just stays the same. It's constant. No, at any given time, some of the some of the nitrogen dioxide is being converted back to dinitrogen tetroxide. And some of the dinitrogen tetroxide is being converted to the nitrogen dioxide. So that's what they mean by dynamic, is that the forward rate is still happening and the reverse rate is still happening. And I think a lot of people have difficulty with that, especially when we look at a physical process like you've got a cup of ice. So here's your ice cubes, and you have water. And so what you have here is you got an equilibrium between H2O liquid water and you have H2O solid ice. Well, there's a dynamic equilibrium here. At any given time, some of the water is being converted to ice and some of the ice is being converted back to the water. That's what we mean by equilibrium. It's dynamic, and as long as there's ice present and there's water present, there is a dynamic equilibrium. So the same thing here, as long as there's nitrogen dioxide present and dinitrogen, dinitrogen, they're not really showing that, dinitrogen tetroxide present, then there's going to be a dynamic equilibrium. All right, at equilibrium, this is the most important, I think, of these. At equilibrium, the forward and reverse reactions are equal. All right, the forward and reverse reactions, the rates of the forward reaction and the reverse reaction are equal. And you go, why is that? Well, if the forward reaction isn't equal, then we're going to continue making product, and the reactant's going to decrease. And if the reverse reaction isn't equal, then the product is going to be converting to reactant, and so we would see this huge increase in reactant, and we'd see a decrease in the product. So these rates have to become equal. They have to become equal. So at equilibrium, the rates of the forward reaction and reverse reactions are equal. Make sure you understand that. Equilibrium can be established starting with only the reactants, starting with only the products, or a mixture of both. So everything we've done in chemistry up to this point is we've always started with reactants and we've had zero products to begin with. Well, that we're going to see examples of where you're going to have a certain concentration of reactant and a certain concentration of product. That means a mixture of both are present. Sometimes we're going to start with, even though this is the reactant, we're going to have zero reactant, and we're going to have some product initially. And so you know the reaction is going to go that way towards the reactants because you don't have any reactant to begin with. So if the reaction's reversible, this reaction can happen. So that's the what throws students the most, because like, isn't this a reactant now? No, we defined what the reactants and products were, and we just have a concentration of product and no reactant. So be cognizant of that. It happens, and I find students kind of struggle with that because everything we've seen up to this point has always been some amount of reactant, no product, especially when we did stoichiometry and Gen Chem 1. All right, so calculating the equilibrium constants, magnitude, size of the equilibrium constant. How large is it, and what does it mean? That's what we're focused on in this section. All right, so here we go with what we just said. The rate of the forward reaction and the rate of the reverse reaction are equal. And you go, why is that so important? Because now what we can do is we can set the rate law for the forward reaction equal to the rate law of the reverse reaction. And then we're going to solve for the rate constant forward divided by the rate constant reverse. And when we do that, so mathematically do that, manipulate it. You might as well get used to doing some math here. Manipulate this equation so it looks like this. Can you do that? So we get this. We combine the two rate constants together, and that forms an equilibrium constant. And the equilibrium constant, notice, is a capital K. And then the lowercase c means we're dealing with concentrations, not pressures of gases, and we'll see that later. But when you see a C here, it means concentration. And you know it means concentration because in the last chapter we said that if you have brackets, then that means concentration of moles per liter, which we call molarity. Now here's the other thing that's really important about the expression. It is always the products in the numerator and the reactants in the denominator. Once we mathematically manipulated this up to this, notice the products are in the numerator and the reactants are in the denominator. Another thing I want you to think about here is we're going to be talking about the ratio here, the ratio of product over reactant, which gives us the equilibrium constant. So we're going to be comparing one ratio to another, one set of conditions to another, and comparing the ratio of product to reactant to see where equilibrium lies. So just keep that in mind. That's going to be important as well. So again, last slide, last couple slides back, really important, those postulates. And then this slide's important in showing you how we go from kinetics up at the top here to now we're going to focus on equilibrium from here on out. So the simplest problems that you're going to have on this is, just write an equilibrium expression, and because it's just the products, and it is actually the stoichiometry of the products divided by the reactants concentration to the stoichiometric coefficient. So we'll see that in a minute. All right, so this is what you may be doing a lab like this in class or in lab. So an exercise like this in lab. So this is the way this works. So again, what do you have? You have to have a balanced chemical equation. So here's where stoichiometry kicks in from Gen Chem 1. And so the reaction has to be reversible. And so we have our reactants and our products. And we could say aqueous here or gas. I can't remember. Oops, I don't remember what it was. Let's see. Let's go back to be sure. It is aqueous. All right. So aqueous means these substances are dissolved in water. All right. That's what aqueous means. So here we go. Initially, we have this concentration of dinitrogen tetroxide. We have 0 of the product, which is pretty common, right? That's what we generally think of. And then we let this settle down to where the rates become constant. We find that these are the concentrations at equilibrium. We plug these concentrations into the equilibrium expression. That's what this is called. And that solves for the rate of the equilibrium constant. I'll keep making that mistake from time to time. It is an equilibrium constant. It's a capital K. Capital K equals this. Capital K at concentration. So notice the second reaction, we initially start with some dinitrogen tetroxide, but we also initially start with some product, nitrogen dioxide. At equilibrium, we get these concentrations. If we plug these concentrations into this equation again, notice we get the same equilibrium constant. And that's why it's called an equilibrium constant. So it doesn't matter what these concentrations are initially, they will settle at when the rate of the forward reaction equals the rate of the reverse reaction. We have those the equilibrium concentrations, as they're called, equilibrium concentrations. And notice when we plug them into the equilibrium expression, all of these come out to be a constant within experimental error of 4.6 times 10 to the negative 3. I mean, yeah, you can see there's some variation here and here, and that's experimental error. So that's what's going on. That's what you're going to be doing in this chapter. And then we're going to use this. Here's the other thing. To me, Chapter 15 is the tools chapter. Everything we learn in Chapter 15, you will apply in Chapter 16 and 17. If you don't get Chapter 15 down, you have no shot at getting the materials in Chapter 16 and 17. So I can't stress enough, 15 is really important. This is where we see the mechanics of equilibrium, and then we're going to apply it to acid-base equilibria in Chapter 16, and then we're going to apply it to solubility equilibria in Chapter 17. So it's really important that you get Chapter 15 down, otherwise it'll fall apart later on. All right, so the equilibrium constant and expression. So if I say equilibrium expression, I mean all of this, okay? What they're showing here is it's always the products in the numerator. It's always the reactants in the denominator. And here's what's cool about it is whatever the coefficients are here, that's what you raise the concentrations by. So there's a coefficient of 2 in front of the nitrogen dioxide, so you're going to raise the concentration of the nitrogen dioxide by 2. If there's no coefficient, it's understood to be 1. We don't put a 1 there. So this is what happens, though. When we did the rate law for this, we said the rate law, the only way we know what the orders are is based on experimental data. So if it's first order with respect to the nitrogen dioxide, remember it doesn't come from the stoichiometric coefficient. It has to be experimentally determined, and it just happens to be that it is 1, but that has to be determined experimentally, unless this is an elementary step. If this is just a one-step reaction where this goes from this to this, then I would agree that the stoichiometric coefficients equal the orders with respect to the concentrations in the rate law. But when we're in equilibrium, when we're doing equilibrium problems, yes, the coefficients go directly to be the powers for each of the substances. So it makes it easier, but I just find students after they've had kinetics and then they start this, they get the two confused. And you say, well, when's that going to be a problem? Well, it's definitely going to be a problem when you take the final exam, the comprehensive final exam. All right. This is another really important slide. I think a lot of students don't understand, and so let's talk about this slowly. What is the reaction quotient, QC? So it says it's the fraction with the product concentrations in the numerator, the reactant concentrations in the denominator. So that looks just like an equilibrium constant, raised to the powers equal to the corresponding stoichiometric coefficients. So all that sounds exactly like equilibrium, but here it is. The reaction quotient is what you have before equilibrium. You plug in those initial concentrations of the products over the reactants raised to their respective coefficients, like you see in our general equation here. And if it's not at equilibrium, then it's called reaction quotient. If these concentrations equal the equilibrium constant, then you've chosen concentrations that are at equilibrium. Now that usually doesn't happen. So what we're going to be doing is comparing the initial concentrations placed in this equation. We're going to compare that to the equilibrium constant. So that's what we're going to be doing, comparing reaction quotient to equilibrium constant. Again, what's the difference? If it's not equilibrium concentrations in the expression, then it's called reaction quotient. If these concentrations equal, when we plug that in, if it equals the equilibrium constant, then those are equilibrium concentrations. Another thing that throws students is all of this stuff about equilibrium. There's a name for this. It's called the law of mass action. It's an older term. I don't hear it used as much, but make sure you know that equilibrium is also called the law of mass action. Pretty much what it's saying is, we know according to Gen Chem 1, Dalton's atomic theory, matter cannot be created or destroyed in a chemical reaction. So all matter has to be accounted for in a chemical reaction. And so some of the reactants lost and it forms product, and maybe some of the products lost and forms reactant. But all the mass that if you start with 10 grams of reactant and 0 product, and then a reaction happens and you only have 5 grams of reactant, there better be 5 grams of product in the box as well, because you can't create or destroy matter. So law of mass action. All right, so you're going to get a chance to do a problem here. And so what I would tell you to do here is read the problem, work it out on your own based on what we've lectured on. If you can do this, you're in good shape. If you can't, you need to read that section of the book over and over again. All right, so stop there. All right, welcome back. So this is what you're going to be doing. It's a lot of organization of data in this chapter, and 16 and 17. So the first thing we have to have in order to do any equilibrium problem, so all this is description up here, right? It's all description about phosgene gas and why they banned chemical weapons after World War I. So here we have our balanced chemical equation. Carbon monoxide reacts with chlorine gas to form carbonyl chloride. All right, so we learned how to write balanced chemical equations in Gen Chem 1. And make sure you put the phases of matter. That's important. That's going to be important too. And then we see this reaction is reversible. So there's something we're going to focus on. We don't see the arrow just going one direction. It's going both directions. That tells us the reaction is reversible. All right, so it says in an experiment conducted at 74 degrees Celsius, the equilibrium concentrations of the species involved in the reaction were, all right? So here's what I want you to focus on. It says the equilibrium concentrations of the species involved. So they're telling you these are equilibrium concentrations. These are not initial concentrations. So you have to make sure you pick that out of the problem, because if these were initial concentrations, then we'd be solving for QC, but they say they're equilibrium concentration. So what we're going to be solving for is the actual equilibrium constant here. Okay? So the first thing you need to do is write the equilibrium expression for this reaction. And you should have capital K You should have a subscript C to say, hey, I'm talking about concentrations, not pressures here. Equals, we have one product, carbonyl chloride, and we divide that by our reactants, carbon monoxide concentration in moles per liter and the chlorine concentration in moles per liter. That's my equilibrium expression. Then what I will do is I will plug in these values for carbon monoxide, for chlorine, because these are equilibrium concentrations, and plug that in for the carbonyl chloride, and I will solve for that, and that should give me the equilibrium constant. So hopefully you've done this problem. These are easy problems. I will have on a quiz and an exam just for you to write the expression. That's worth just as much points as the hard problem, so make sure you can do this. They plugged in the values. They get this for a number, but you can only have two significant figures. Watch your significant figures because these only have two. And so that's the final answer. Notice there's no units with that. It's just that number. The units are meaningless here. There's a lot of discussion on that, but there are no units for this. It's just 2.2 times 10 to the second. Now, here's what I want you to get out of this. The larger the equilibrium constant, the more the products are favored over the reactants, right? To get a number like 220, I mean, that's what that expands out to, right? That means the numerator has to be larger than the denominator. So that means the product is favored over the reactants. That's going to be an important concept that you're going to carry with you throughout this chapter 16 and 17. The larger the equilibrium constant, the more the products are favored. Just keep that in mind. All right. So here it says calculate the equilibrium constant. So they say we find it useful to calculate QC, the reaction quotient. And the reason why we want to calculate non-equilibrium concentrations, plug those in here, and determine QC, is that's going to give us an indication whether the reaction is going to go in the forward direction, the reverse direction, or we just happen to pick an equilibrium value. All right, so that's what's important about QC. This is super important because this is how you're going to determine the direction the reaction is going to go. All right, so what this graph is showing is, again, we're sticking with our balanced chemical equation of dinitrogen tetroxide is decomposing into 2 moles of nitrogen dioxide. So initially, it's all, so this reaction is a little different. So initially, they're saying it's all nitrogen dioxide. So we just have product initially. And we have 0 of the reactant. All right. And so as the reaction progresses, look what happens. So initially, we have all nitrogen dioxide. So you know this reaction is going to go in the reverse direction. Why? Because you don't have any of this present initially. In fact, it's undefined. But that tells you that this is going to be consumed and this is going to increase. And so that's what we see. Then dinitrogen increases. So over time, you look at Q here, and Q at this point in time is 0.080. So what I want you to know about this part right here is Q is greater than the equilibrium constant. You go, well, what's the equilibrium constant? Well, we assume there's no change out here, so we're going to assume, even though that's Q, that's pretty close to the equilibrium constant. And 0.080 is greater than 4.63 times 10 to the negative third. So I don't know that that's the equilibrium constant yet, but it's pretty close compared to that, because you can see the change is not starting to not. We're starting to see that the rates of the forward and reverse reaction are equal. So this is a classic example of why you have to calculate the reaction quotient to determine which way this reaction is going to go. Most people always say, oh, always going in the forward direction. No, not in this case. In this case, you had nitrogen dioxide concentration and you had 0 of the reactant, and the reaction has to go in reverse because Q is greater than K. Good problem. All right, so here's your easy problems on the test right here. Quiz, test, whatever. This is quick recall. All you have to do here is write the equilibrium expressions for every one of these reactions. All right, write the equilibrium expression for each one of these reactions. I'll do the first one, then you ought to stop the video and do the rest of them. All it is, it's this easy. You just say K at concentration equals the concentration of the ammonia raised to the second power. Why? Because there's coefficient of 2 here. Oops, I shouldn't have gone that far over. Forget that part right there. All right, equals over here we have N2, concentration of the nitrogen, times the hydrogen cubed. And technically, well, that's fine. You can do that. There you go. That's all you do. All right, so stop here, do the rest of them. Oops. All right, let's go back. They asked you to calculate the reaction quotients. Oops, I calculate the equilibrium expressions. See, I made a mistake here. It says I didn't read that close enough. Reaction quotient. So you set those equal to QC, not K. All right, I'll go with that. So here's what they look like. Doesn't affect the expression other than instead of K, it should be a QC. And this is what you should get. And if you got these correct, you're in great shape. Easy problems. Just make sure they're Q's, not K's. It's always reactants over products. I mean, products over reactants. Oh my gosh. Products over reactants. I'm getting close to the end of this video, I can tell. All right. So let's read these rules. One of the things the equilibrium constant tells us is the extent to which the reaction proceeds at a particular temperature. So you can see equilibrium constants are temperature dependent, just like rate constants were. The reaction will go essentially to completion, and the equilibrium mixture will consist predominantly of products. That's one possibility. All right, the reaction will go essentially to completion. That means the reaction is going to go mostly this way, maybe a little this way, but essentially goes to completion. All right, and so if it's mostly going this way, that means mostly product is going to remain at the end of the at equilibrium. Let's say that. So the other time is the reactants will not occur to any reaction will not occur, and the equilibrium will lie predominantly with the reactants. So that means this reaction lies closer to this, and very little forms product. And then we have where both the reactants and the products are about equal concentration at equilibrium. You go, why do I need to know this stuff? Well, again, if you know, I know I know a lot of people are not from Lexington, Kentucky, but let's talk about Nicholasville Road on Lexington, Kentucky, to show you how equilibrium works. You notice when you come into town in the morning, there's more lanes that are going into town. So you're going to get an equilibrium, but it's going to be predominantly everybody going into town, easier to get into town. And then in the evening, they change it the other way. There's more lanes going out of town, less lanes going into town, so that gets people out of town. And then if you got the same number of lanes going in and out of town, it's going to be a mixture of both, right? So you go, why do I need to know this? Well, this is how Lexington was able to move a lot of traffic without expanding Nicholasville Road to 8 lanes both sides and taking up the houses and hospitals and everything else on both sides. So You have a given number of lanes and you change the direction of them to affect the equilibrium. Really neat stuff. They've won awards for that. All right, so let's look at this problem. When the magnitude of K of the equilibrium constant at concentration is very large, what do we expect? Do you think at equilibrium you're going to have mostly reactant or you're going to have mostly product? How you're going to determine that is write the equilibrium expression. So the product is this silver ammonia complex. And the reactants are the silver ion concentration and the ammonia concentration. Don't forget the 2 there, coefficient of 2. So you know to get a number that large, 1.5 times 10 to the 7th at 20, remember temperature is important, at 25 degrees Celsius, this number has to be huge and these numbers have to be small. So that tells you at 25 degrees Celsius, the product is going to dominate at equilibrium. Now, that may change as we change the temperature. That's why they have to quote the temperature. You have to quote the temperature because equilibrium constants are temperature dependent. All right, so when the magnitude is very small, look at that number, 4.3 times 10 to the negative 25th. Well, again, you write the expression for this. It's equilibrium constant concentration is the nitrogen oxide to the second, and then the nitrogen gas concentration times the oxygen gas concentration. And there's over 1 to 1. So again, to get this kind of number, the denominator has to be huge and the numerator has to be small. So as this gets larger, just think about, just keep the number up top fixed at 1. What happens when it's 100? What happens when it's 1,000? What happens when it's 1 times 10 to the 6? So the overall ratio gets smaller. We get this for the value. All right. To get that kind of small number, this has to be huge in the denominator, very small in the numerator. All right, so here's the other rule. This is the tricky one. If it's between 100, if the equilibrium lies between 100 and 100th, which is 1 times 10 to the negative 2, then you're going to have both a mixture of reactants and products. All right? You're going to have a mixture of reactants and products. So that's where it gets a little tricky. You know, this is where pharmaceuticals cost so much money. Like, you spend a lot of money and you form just a little bit of the product and you take that off, you take that product off, that's the active ingredient in the drug. But then they have to load this up more and more just to get that little bit of product. Whereas something like the first reactant, the first expression, where this is such a huge number, product is favored. If that product is the active ingredient in the pharmaceutical, then that's probably pretty easy to make, and it you know, there's profit to be made there, unless the reactants are super expensive or something like that. But even that's a much better case scenario than either this one, which says very little of this is going to be formed, or even the mixture where you're still going to have to purify the product out of this mixture. All right, that's where we're going to stop at today. I think that's long enough. I know these lectures are long. A main thing to do is just watch a little at a time, 10 minutes. If you can handle 40 minutes, fine. But I know that about 10 minutes is most people's break point. So a little 10 minutes at a time. Read the text. I can't stress that enough. You're not going to be successful in this class just listening to this lecture. I'm just guiding you through it, trying to hit the points that I think students have trouble with. But you got to read the text, and you got to write that in your journal, especially those definitions in bold. You got to speak the language of a chemist, and things like reaction quotient means something different than equilibrium constant. So we'll stop here and we'll pick up on this in the next lecture.